All right, part two. And the only reason why I needed to do part two was because I turned the page and I realized the lesson kept going. But at least we broke it up into like a calculator part. And now let's go with non-calculator. So remember before when we were doing it in the calculator and we graphed it, it showed the shading under the curve. And that's the idea. It's that area under the curve. Now, it could be negative if it was below the x-axis and positive if it's above. So it's about that area under the curve. So what are we going to do without the calculator? Well, here's the idea. We can graph it. So in this one, we don't have the graph for us, so we're going to have to graph it. Now, 2x minus 1, absolute value, that means it's a v. What happens is if you want, you can plug in numbers, knowing that we're taking the area from 0 to 3. So 1, 2, 3, okay? Now, if we talk about what happens at 0, if we plug in 0, we get positive 1. So I know I have a point there. Now, if I plug in 1, well, what do we get? If I plug in 1, I get 1 again. So I need to remember that when I do my v here, I need to figure out where this v, the vertex, is coming from, okay? All right, so that vertex there is 1/2. In other words, when is it 0? So 2x minus 1, where does that equal 0, right? And we get x equals 1/2, okay? So this is at 1/2. We also know, because we're ending at 3, I want to know where this happens to end at 3. So if I plug 3 in here, 2 times 3 is 6. 6 minus 1 is 5. Okay, if we talk about the area under the curve, we have to remember the shape. So if you look here and I say from 0 to 1/2, there's a triangle right there, a right triangle. And from 1/2 to 3, there's also another right triangle. So what we're going to do is we're going to add these areas together. Okay, we find the area under the curve, so we have two areas of shapes we know how to get, right? Because what's the area of a triangle? 1/2 base times height. So let's talk about this first triangle. 1/2 times the base is 1/2. And the height, again, is 1. So that's the first triangle. We're going to add on the second triangle. The 1/2 times the base. The base in this case is 2.5. 2.5 is 5/2. I'm doing that so that way it's easier to do the math without the calculator. Times the height, which in this case is 5. So 1/2. We can actually keep this as our answer because remember, we do not have to calculate it all the way. But we could do this 1/4 plus, what is that going to be? That's going to be 25/4. So 26/4 is our area under that curve. So that's the idea of an integral. An integral shows us the area under the curve. If we are not using a calculator, we are hoping that the areas under the curve create geometric figures that we know how to calculate the area for. So 6, set up. So just as set up, we're not solving, we're setting up. Set up a definite integral which could be used to find the area. So we're just setting it up. The function is 2x squared minus 3x plus 3, and we're going from 0 to 2. So remember that it's the integral. It's our lower boundary, or where we start, which is at 0, to where we stop, our upper boundary, which is 2, of our function. And don't forget that since we are taking the integral, that this function actually is dx. Okay, and that's it. That's all we had to do. Now down here, we're going to discover the fundamental theorem of calculus. Of course, after this, we're going to be able to do it a little bit quicker, but this is where it comes from, okay, guys? So we're going to find the integral from 0 to 5 of f prime of x, and this is f prime of x. Remember, the integral is what? It's the area under the curve. So if I draw a line straight down where I'm ending, which is 5, and I find the area under this curve, do you guys see that it's a rectangle? How do you find the area of a rectangle? Well, base times height. So base times height. So this means the integral is 15. All right. Write an equation for f prime of x on 0 through 5. Well, what does that mean? F prime of x equals, well, the prime, the derivative is where it's at, right? It's the slope of your original graph. Well, what is this telling me? The slope is always at 3. Part C, find f of x if 1 equals 4. Okay, so now what we're going to do is we're going to take our f prime of x function, right? And then we're going to take the integral of it. Remember, the integral of a function or of a constant, we hook on the variable, and don't forget, we don't know. In this case, it's our indefinite, so it's plus c. Now we're going to plug in. So f of 4 equals 3 times 1 plus c. So c equals 1, which means f of x, or our original function, would be 3x plus 1. Now what we're going to do is take our f of x and say f of 5 minus f of 0. Okay, well, f of 5 in here would be 3 times 5 plus 1 minus 3 times 0 plus 1. Let's see what we get. That means we get 16 minus 1, which is 15. And what do you know? That is the area under the curve. So we're defining how to take the integral algebraically instead of just finding the area under the curve. Okay, let's do it again and see what happens here. So we're finding from negative 2 to 1 of f prime of x. Okay, so from negative 2 to 1, if you see here, guys, we have a triangle. But area under the curve. So actually what I did is just wrong because, let me erase that, because it's the idea of it to the x-axis. So here, we have it reaching the x-axis right here. So there's a small triangle right here. And then we have another one right here. So it's only to the x-axis. When we talk about area under the curve, it's only to the x-axis. I made that mistake on purpose before because I don't want you just to take the whole thing. Area under the curve to the x-axis. All right, so this triangle right down here. Oh, and what did I do? I did it again. And I'm glad I'm doing this, guys, for the fact that these are mistakes. Is this to the x-axis right here? Was that under the curve? Actually, if you look under the curve to the x-axis, it's right here. Those are mistakes that happen all the time. Okay. Sorry, I know I keep making you erase. So if we look at this triangle right here, I have 1/2, the base is 1, and the height is 2. Now, because it's under the x-axis, this is going to be a negative area because it's under the x-axis. Then we're going to add 1/2. The base here is 1, 2, and the height is 1, 2, 3. Did I count wrong? Yes, I did. 1, 2, 3, 4. Ooh, I didn't go up all the way, guys. Okay, when you calculate this all out, we get the value of 3. Okay. Now we're going to write an equation for f prime of x on this interval. So from here to here, what is this function? Well, it's linear, right? So what is the slope? The slope is 2, and it goes through 2 on the x-axis. So that is our function for that f prime of x. So what we're going to do, just like we did before, is we're going to take the integral. Okay, we're going to find that out. So f of x, here's our power rules, right? So we get x squared. Okay, now I'm going to add 1 and divide by that, but the 2's cancel. So that's why I get x squared plus the constant, the integral of a constant, we add that variable to it. And then, of course, we need to do a plus c. Now let's see what that c value is. So we have f of 1. Oh, and this should have been 4, right? What is with me, guys? This should be the value of 4. So when x is 1, it equals 0. So 0 equals 1 squared plus 2 times 1 plus c. When we solve this out, you get c equals -3. So this means our function of f of x equals x squared plus 2x minus 3. Now we're going to plug in our 1 and plug in our -2. When we plug in our 1, we get 1 plus 2 minus 3 minus, now we're plugging in our lower, which is -2 squared plus 2 times -2 minus 3. So when we plug that in, what do you know? We get the value of 3. Okay, so we are able to find the area under the curve by taking the integral and plugging in our lower boundary and our upper boundary. Specifically, our upper boundary minus our lower boundary. All right, let's see what else we can do here. Given that x of t is -1/2 t squared plus 4t minus 3 is the position equation for the object on the x-axis. For the displacement of the object, find the displacement of the object on the interval 1 to 4. Remember, the displacement is about what position you end in minus where you started. So pretty much what we're doing here, guys, is we're saying f of 4 minus f of 1. And it's not f, it's x, because that's our function value. There we go. All right, so when I plug in 4, I get 5. When I plug in 1, I get 1/2. So 5 minus 1/2 is 9/2. So this is the displacement. Find the velocity equation. Remember, velocity is the derivative of the position equation. So velocity, bring down the 2 and the 1/2 cancels, so negative t, that would be plus 4, and the minus 3 goes to 0. Now we're going to sketch the line here because it's linear. So at 4 we have our y-intercept, and then we are going -1. Okay, we sketched it. Now look, we're going to find the integral. In this case, we're going to do it by the area under the curve. And it is a triangle to our x-axis. So we get 1/2. The base is 4. Nope, sorry, because we're going to 1. Boundaries are very important. So we're going from 1/2 the base. The base is going to be 3. And the height, if you look, the height actually goes here, which is 3. And what do you know? We get our 9/2. Okay, so we're able to find the integral, the area under the curve, by doing that algebraically. So let's talk about that, what that really means mathematically. The idea is, this is the fundamental theorem of calculus. If f prime is continuous on the interval a to b, then the integral from a to b of f prime of x dx equals f of b minus f of a. I wish I had my highlighter right in this, because I want to point this out to you guys. There it is. Okay, so when we see a problem just like this, we can solve it by taking the integral and saying the upper boundary minus our lower boundary. This is the way to write it when the in-between steps. So when we find the integral, we're not going to add on c because this is a definite integral. We have our boundary still right there. So I'm going to show you now algebraically how we can write this down instead of finding the area under the curve, because it could get really messy, right? All right, so the first thing I'm going to do, of course, is I'm going to rewrite this so I can use my power rule. We get the integral from 0 to 4 of 2y to the 1/2 plus 1 dy. So I'm going to take my integral. Sorry, my pencil's running out of stuff. Okay, so if I look at my integral, I'll keep the 2 there. Y, I'm going to add 1 to the exponent, which gives me 3/2. Dividing by 3/2 is the same thing as multiplying by the reciprocal, which is 2/3. Okay, now I have to take the integral of 1. Well, that's just y. Now, before, we were saying plus c because we were doing the whole thing, but right now we have boundaries. So the way to write that is to do your line and to keep your upper and lower boundary. Okay, so what that means now is that we're going to plug in 4 minus plugging in 0. So I'm going to write that out. Excuse me. So I have 4/3 times 4 to the 3/2 plus 4. Okay, so that's plugging in the 4 minus plugging in the 0. Well, if I plug in 0, I get 0. Plug in 0, I get 0. 0 plus 0 is 0. And you can leave it like that, especially if it's a free response, so you don't have to worry about simplifying. Okay, let's try that again. on number 11 here, we're going to actually use a U substitution just to make this a little bit easier on ourselves. When it comes to U substitution, we're actually going to change our boundaries so we don't have to plug back in the U. Okay, I'm going to repeat that. When we were using U substitution before with our indefinite, right, no boundaries, the plus C, we had to plug back in our U into the equation. But since we have boundaries, we're actually going to change our boundaries so we do not have to substitute back in. So I'm going to show you how to do that now. So U equals our 4t plus 1. Take our derivative, we get du. Oh, and I should say t, but it's du. No, du equals 4 dt. So I'm going to solve for dt so I can replace it, right? So du divided by 4 equals dt. Now I'm going to substitute back in. Right now I'm not going to do my boundaries yet. I'll show you those in a minute. I have u to the 5th du all over 4, which means actually I can pull that 1/4 out front. Okay, now I have to change my boundaries so I don't have to plug that u back in. To change my boundaries, all I do is I put my boundaries into my u. So 4 times 1 is 4. 4 plus 1 is 5. 0 times 4 is 0. 0 plus 1 is 1. So now because I changed my boundaries, I do not have to plug back in that u substitution. So that 1/4 stays. Now I have my power rule of u to the 6th, and I divide by that exponent. And my boundaries being 5 and 1. Now I just have to plug my upper boundary minus my lower boundary. So I have 5 to the 6th over, well, 4 times 6 is 24, minus 1 to the 6th over 24. And voila, all done. If you wanted me to prove that later, that you don't have to plug in the u because we changed our boundaries, I can do that. But if we did not change our boundaries, we would have to substitute the u back in and then plug in those old boundaries. Okay? Number 12. So my u, remember the u is always under, it's the more complicated one, the one that's under the square root. So we're going to have u equals 2x minus 1, which means our du equals 2 dx. Solve for dx, so du over 2 equals dx. Okay, got to be careful though, right? Because that 1/2 comes out front. There's our integral. And yes, our u is right here. But we still have an x up there. Do you guys remember how to do that? Remember, we have to want it in u's, right? So we have to solve for x. When we solve for x in this u here, I get u plus 1 all over 2. Wow, that's getting a little complicated there, huh? All right. Let's change our boundaries. Remember, plug that in. So 2 times 5 minus 1 is 9. 2 times 1 is 2. 2 minus 1 is 1. Okay, this is good here. Let's put this on top as u to the 1/2 plus 1/2. Not to the 1/2. U over 2. There we go. Okay, because that was our x. You guys see what I did there? Okay, now let's simplify. We need to bring this up here, right? So what we're saying, and I'm going to write it all out, we're saying 1/2 times 1/2 integral 9 to 1. I have this u over 2 plus 1/2 to the negative 1/2. Oh, and this should be du. I forgot to use there. Okay, everybody see what I just did? Oops, I forgot u to 1/2. Bringing the u up to the negative 1/2. Okay, can't take the integral yet because remember I have to multiply that out, distribute it out to be able to use the power rule. But one of the things I want you guys to see here is this both has a 1/2 here, right? So I can actually stick another 1/2 out front. You guys see that? So if I stuck another 1/2 out front, well, 1/2 times 1/2 is 1/4. Integral 9 of 1. That leaves me with u plus 1 times u to the negative 1/2 du. So I just moved another 1/2 out front. Now let's distribute that. I get 1/4 integral 9 to 1. Remember, what did we do to the exponents here? We add them. So I end up getting u to the 1/2 plus u to the negative 1/2 du. Now I can use my power rule. I'm going to try to give myself some room. Okay, I'm going to bring that up here. So I'm going to take the integral now. Remember that 1/4 is out front, and it's multiplied by everything. So add 1 to the exponent, divide by that exponent. Well, dividing by 3/2 is the same thing as multiplying by 2/3. Plus, add 1 to the exponent, divide by 1/2, which is multiplying by 2. Okay, and I still have to write this properly because we have boundaries. Boundaries are 9 to 1, or 1 to 9. Now I don't have to substitute that u back in, right, because I already changed the boundaries. So we have 1/4 times 2/3 times 9 to the 3/2 plus 2 times 9 to the 1/2 minus. Now remember, the 1/4 goes with both boundaries, guys, so minus 1/4 times, now I got to plug in that 1, so 2/3, right, because 1 to anything is just 1, plus 2, and we're done. We don't have to do anything more unless it wants us down, break it down to one single number. But if it's open-ended, you can leave it like this and you're done. This is showing you what you're doing here. Okay, let's do something with trig just to see how we are doing. And still do the u substitution. So u is 2x, which gives me du to be 2dx. Solve for dx, we get du over 2 equals dx. All right, let's substitute back in. So integral, that 1/2 comes out front. Cosine of u du. We've got to change our boundaries, right? So pi halves times 2 is pi. 0 times 2 is 0. Okay, what's the integral of cosine? That would be sine u boundary of pi over 0. Plug in, so we get 1/2 sine pi minus 1/2 sine 0. Now, of course, we could break this down. This is a little bit easier to do in our head, because sine of pi is 0. 0 times 1/2 is 0. Minus, well, sine of 0 is 0. So the area under the curve is 0. Yes, this is a lot to get used to, I know. Okay, this one. The only way you know how to use this is to recognize what is going on. So remember that this is the fundamental theorem of calculus, right? We're saying that we could find the area under the curve by taking the last position minus our first position. What happens when it's a non-calculator part and we can't take the integral because it's some weird thing? Well, hopefully our integral is actually the value is given to us. So what happens here is we can find our ending position by knowing our starting position and our area under the curve, okay? So find end position. How I always recognize this type of question is when I see that I'm given either the f prime of x or the area under the curve, a starting position, and I want to find an ending position. Okay? So I can say that f of 2 equals our starting position, f of 0, plus the integral from our start to our finish of f prime of x, which in this case is 3x squared plus 3, and then dx. Okay, now luckily this is power rule, so we should be able to solve this. So f prime of 2 is what we're solving. F of 2 is what we're solving. F of 0 we have, so I get 4, right? Now what I'm going to do is take the integral and do that boundary. So plus, this is a power rule, so this becomes x cubed plus 3x, and we're going from 2 to 0. So now I'm going to calculate that out. I get 4 plus, plug in our 2 first. So 2 first would be 2 cubed plus 3 times 2 minus, plug in our 0. Well, 0 plus 0 is 0. And we get our value of 18. So our starting position is, or actually in this case, our ending position, starting was at 4, our ending position's at 18. Okay, let's do it again for number 15 here. If the object's velocity is v of t, find s. Okay, how are they related? V is velocity, s is standard. Velocity is the derivative, so we have the derivative. Let's set this up. We're finding s of 2, which equals our starting plus the integral from our starting to our ending of our functions, or v of t, I should say, dt. All right, so guys, in this case, we don't know this. We don't know how to take the integral over power. So with this one, you would definitely be able to use your calculator. Okay, so what I want you guys to keep in mind, though, is that we're saying S of 1 is 8. So we're actually going to type all of this in our calculator to give us our position, because we cannot take the integral by hand. Okay, so let's get down here. So we have 8. Now do it all at once, just in case for decimal. So 8 plus math integral. And we're going from 1 to 2. Again, I know that because of our values right there. Of our function 2 to the 3. I'm going to say x and just keep it in x's even though we're in t's, okay? Squared minus 5. And then, again, I'm in x's. Okay, do you guys see that? Enter. And of course, how many decimal places do we go out? We go out 3 decimal places, so 24.502. These are the ones you need to recognize because we're finding an ending position by given the first position. Now, could we switch this around? Could we be given the ending position and we're finding the beginning? Yes, but let's see what happens when we get there. Okay, guys? This is a lot of work, a lot to practice. Take your time, ask those questions, work together.